Welcome back. We were talking about the fade mitigation technique, and mainly we came up to signal processing FMT, that is signal processing fade mitigation technique, after discussing the power control technique. So we go to this signal processing FMT on the modulation. We have seen the spectrum efficient modulation needs higher power, that is higher order of PSK, which is in one symbol itself many bits can be put together, which is maybe 8 phase PSK or 16 phase PSK or 32 phase PSK. You can have a spectral efficient modulation, but that needs, for a particular BER, that needs higher power. Now during the fade, we have seen from the curve, that is during the fade there will be attenuation. To maintain the same BER, we can use a lower spectral efficient modulation that could be used to compensate for lower EB. Because of the fade, the EB has reduced, C has reduced, means the energy per bit EB also has reduced. So from higher spectral efficient modulation we come down to lower spectral efficient modulation. So bandwidth will be, requirement will be more, but we can manage the fade. There is the other technique, is if you recollect, it was C by N naught is equal to EB by N naught multiplied by bit rate, or ES by N naught multiplied by symbol rate. So when the C by N naught has gone down, we can manage the same EB by N naught or ES by N naught by reducing the data rate. So data rate reduction is another technique. So data rate is directly proportional to the C by N naught, and data rate reduction is obviously gives certain gain in the CDMA, that is code division multiple access. I hope some of you have studied this, otherwise we will see this one when we talk about multiple access techniques. So where the data is spread using a code, and the advantage is coding gain. What we get, it depends on the how much is the spread divided by the data rate. So as if you reduce the data rate, your gain increases. So coding gain has that can increase, and that can compensate for fade. So CDMA technique can be used. Now these all signal processing, which includes the coding, the modulation and the data rate reduction, needs a certain closed loop operation, obviously, because the system is operating, let us say between hub and a remote terminal. Signal communication is operating, and the communication takes a fraction of a second, almost 250 millisecond, going up and coming down one hop. Now if the hub changes the modulation, coding or the data rate, suddenly the remote terminals, they do not know. So you should know, the remote terminal should know when to change, and also what is the quality is reducing at the remote terminal, that has to be monitored first, and then change has to occur. So therefore there has to be closed loop operation between the hub and remote terminal, or remote terminal to remote terminal, for all signal processing FMT. The other technique of FMT is the diversity. It is common sense, that is, if I use a site diversity, and the signal path which right now we are using might be having certain impairment, use another signal path where this impairment is not there. So you change the site, it is called site diversity, either on the ground or on the orbit. So we can call it a orbit diversity. And also we have seen from the attenuation curve, that is when you go up in the frequency, that is from Ku band to Ka band to B band, when you go up in the frequency, your attenuation is much more. Say we are operating at a higher frequency band, and because of attenuation, either you can use power control or you can change the frequency itself. So the operation frequency can be changed, but each has their advantage and disadvantages. Or the other one is time diversity, that is when you are operating, that time some impairment is happening. The impairment may not be existing continuously, so it will go away after some time. So you start communicating after some time. So that is called time diversity. The site diversity is shown here pictorially, simple. That is the wanted path through which you are communicating has certain, here a cloud is shown, actually impairment. So you select another path where this attenuation is not there, or this impairment is not there. Now the distance between these two, and you have to synchronize the communication between them. The distance between these two should be such selected, because it's not mobile, it's a fixed station. So such selected based on the historical data of how much this impairment spreads over this region. It may be a few kilometers, it cannot be in meters, it will be few kilometers or few tens of kilometers sometimes. For highly reliable links, people use this type of system. We'll show you very quick some models proposed by International Telecommunication Union for these type of diversity. Let us take two sites, site 1 and 2, and joint attenuation at time t is estimated as Aj. That is, Aj, function of t, is minimum of A1t and A2t in dB, and that average single attenuation is estimated as As, that is single attenuation. So Ast is A1t plus A2t by 2, that is in dB. So this As and At, if it is plotted in terms of probability of time, this As plots like this, just a typical plot, and Aj plot is like this. So that you can see at the joint site attenuation, you have for the same probability in time, you have certain gain, you have less attenuation. So this is defined as GD, that is the gain due to diversity. So diversity gain in terms of probability is As minus Aj in dB. But there could be other way, that for a particular attenuation, for some time, I mean for less amount of time, you will get the advantage that is in terms of probability using the joint site attenuation, which is called improvement. So improvement is defined as ID. So diversity improvement is IDA is PSA by PJA. This is PSA and this is PJA. So ratio of that, you get a improvement for a particular attenuation. In terms of probability, in terms of time, how much time you get the link available, whereas here you get attenuation in a particular probability of time, how much attenuation advantage you get, that is in terms of diversity gain. Now these are modeled by ITU, and I'll show you a very quick thing just for information. I'll give you some example also. In addition to attenuation, site diversity advantage also depends on the distance, operating frequency, elevation angle, baseline operating range, a baseline operating angle, etc. Each of them is modeled. Gain due to separation of the distance, GD, is a function of d, distance, and the single site attenuation is modeled as two coefficient a, small a and small b, a into 1 minus e to the power minus bd, where a is given as 0.78 of As minus 1.94 into 1 minus e to the power minus 0.11 As, and b is given as 0.059 into 1 minus e to the power minus 0.1 As. These are modeled available from ITU. And the gain due to operating frequency, that is gain due to separation of distance, GD. Gain due to operating frequency, GF, is e to the power minus 0.025 f is in gigahertz. Then gain due to elevation angle is GE, a function of theta, elevation angle 1 plus 0.006 in theta. Gain due to the baseline orientation angle towards the satellite, because two sites are used, g phi. Phi is the baseline orientation angle with respect to satellite. G phi, a function of phi, is 1 plus 0.002 of phi. Yes, you can see pictorially the baseline is now directly, this phi is almost 90 degrees towards the satellite. If the baseline is slightly differently oriented, so you can see the diversity, this much distance you get, whereas here you get distance, this much distance diversity advantage. So it based on the azimuth towards the satellite, where is the baseline. Now the total diversity gain, G capital D, is a multiplication of all these diversity gains, that is in terms of distance GD, in terms of frequency GF, in terms of elevation angle theta, in terms of baseline angle, azimuth angle G phi. And a quick example is just worked out here just for your information. That is for a station receiving at 20 gigahertz from a satellite at 20 degree elevation, has link availability of 99.9% and experiences 11.31 dB attenuation during day. Now what will be the diversity gain if when a diversity station is added at a distance of 10 km with baseline orientation angle of 85 degree satellite? The reason for showing you this type of just an example is to get familiar with some amount of number, how much advantage we get. You can see this is a Ka band operation, 20 gigahertz, and you can see that there is a diversity distance of 10 kilometer. Availability number is 99.9, and at this 20 gigahertz for a particular rain rate you get 11.31 dB attenuation. So what will be the diversity gain, the number, total diversity gain number? So each of the GD, GEF, G theta and G phi has to be calculated based on the numbers which are available here. Simple. That is, first you calculate the coefficient A based on that model earlier I mentioned, and then coefficient B based on the same model. So using those A and B you find out the GD, then based on the frequency which is in gigahertz you find out GF, based on the elevation angle you calculate G theta, based on the baseline azimuth angle G phi, and multiply all of them, you get 5.84. So with almost, you can see 10 kilometer distance, you get a where your loss was 11.31 dB. With a 10 kilometer distance you get an advantage of 5.84 dB. So almost half of that you have gained with this, just to show you that number. Similarly, diversity, this is diversity gain what you have seen. Similarly, diversity improvement factor can be estimated, that is I is equal to P1 by P2, and that is the probability of at different single diversity to joint diversity is equal to 1 plus 100 beta square by P1. Beta is modeled as in terms of distance, d to the power 1.33 into 10 to the power minus 4. This is again the model given by ITU. And we take another example, almost the previous system number, that is the find diversity improvement factor for 99.9% of link availability and 11.31 dB single site attenuation. Find the improvement in link availability. So first you find two things of diversity improvement factor, and then find whether improvement in the link availability happens or not. So given these numbers you can find out the P1 and then beta square, and then I, which is ratio of P1 and P2, and then the that is the diversity improvement factor, and then link availability is 100 minus P2 because of the P2 site is added. You increase the link availability from 99.90 to 99.97%. So this is another example of improvement factor finding and availability increment of that. Now there are certain conceptual ideas that you can use a different orbit. So the satellite visibility, the wanted link, you have impairment, so go to another satellite. So you have to either use a different antenna or turn the antenna or the earth station, and you have to select such orbit so that impairment does not take place. Normally people do not use this thing. These are that almost a simulation or theoretical ideas. So with the angle theta you get certain orbit diversity. You can have frequency diversity. You have seen that higher spectrum normal operation and lower spectrum during fade. Normal operation you can use higher spectrum with many advantages, and when fade occurs, since the higher spectrum has large attenuation, you come down to another spectrum where this attenuation does not exist or reduces. But then of course you understand the difficulty in this, that you have to have at 2 frequencies complete uplink and downlink chain, both in satellite, both in and ground. And if you have a network, and all the ground system should have this. And availability of bandwidth at lower spectrum is also a problem, because just briefly we have mentioned in one of the slides earlier that at C band we have 700 megahertz roughly allotted by ITU for space to earth, earth to space link, and at Ku band it is roughly of the order of 2 gigahertz. At Ka band is roughly about 2.5 gigahertz. So at higher and higher band you have allotted larger bandwidth. So if you are operating at higher band and suddenly you try to change over to lower band, you may have some problem of bandwidth at the lower spectrum. And then of course, as I mentioned, that additional RF chain with including the antenna required both at the satellite and at each station that is required. Now the other technique is time diversity. Time diversity means similar to retransmission with automatic repeat request, that is at a higher layer. What we do, that is data link control layer. This cannot be used for real time operation. Say you have a audio conversation going on, or video communication or video broadcasting going on. That time you cannot wait, suddenly stop the transmission and wait until the impairment goes away. A rain event is taking place for a few minutes. After that you start discussion on the video conferencing. That's not tolerable. So these are all for non-real time communication that is used. And then these are how much time later you do this repeat transmission or retransmissions or continue transmission is based on the fade repetition rate and the fade duration, which is average value has to be measured earlier, and in real time also it has to be monitored carefully. If you recollect that particular slide where the fade threshold is shown and different fade events and non-fade events are shown. So based on these things, the duration for which the transmission is not going on, that has to be estimated. So mostly it's offline communication, like email. When you do email communication, then this is quite suitable. That's what is listed, suitable for offline data communication application. Now with all these things we have this is taken, a table is prepared by a committee called COS 255, and different type of fade mitigation techniques they have analyzed, and some of them are simulated. And what is shown here is the fade mitigation technique list and average range of the year when the impairment takes place, or I should say the availability, should say non-availability, availability of this FMT, average range of the year, and using that what should be the achievable gain they have estimated in dB, and what could be the limiting factor for each of them. Here this list has to be seen carefully. Some of them are simulated, some of them are experimented. Using uplink power control with a you should look at this particular column, this third column, which shows that maximum achievable gain. For VSATs you get 5 dB, for you can get a 15 dB advantage. You can see this reason is at hub. We will discuss on the ground station when during our topic on ground station. VSATs are very small aperture terminal. So for very small aperture terminal you have all facilities which are available at the terminal are small. So you can't put a very large power amplifier there, since it's a power control, uplink power control. The whatever power amplifiers normally put into the VSATs, you can vary about 5 dB or so. So that's why here it's low. Whereas at the hub, you have a large station, and you have all the available resources for putting 10 times or 15 times more. I mean, much larger than that, and this is in dB. So much larger, 17 times more the amplifier capacity. That is uplink power control. You have different based on different sizing of the terminal you get. Downlink power control, normally satellites, you have a 3 dB gain advantage you put, but the disadvantage in this, if you we have discussed earlier, that you will be operating at normal operation, that is non-fade duration operation, you will be operating at much lower backoff. So even with 3 dB increase in EIRP, you do not enter into the nonlinear region. So normally you will be, most of the time you will see 99.99% of the time you are operating, and only 0.01% of the time you will be introducing these fade mitigation. So rest of the time you will be operating at much lower power, 3 dB less power. To compensate for the downlink power control, you will be using only during this time for 3 dB additional power. Not very advantageous, but this is possible. Now beam shaping is idea level only. Till now very few people have experimented commercially, I am not at least aware. That means you during the fade you change the pattern of the antenna itself, and so that the areas which are getting the fade or rain, there you are providing larger antenna gain by shaping the antenna beam. You don't touch the power amplifier. In that process you save the intermodulation products or adjacent channel interference, but your problem is that the satellite antenna becomes very complex. Normally these are designed with the complex array antenna with additional phase and amplitude adjustment. So these are in the research level. I mean, those days when this cost committee was working, these are the research level. And even now, I am not aware that any commercial things are available. Commercial antenna beam shaping for feed control. Beam shaping is done, but for feed control measure, feed mitigation measure, this is not being used. I think Inmarsat was trying for this. Okay, the other FMT, which is the signal processing FMT, which is the coding and modulation change, and this is commercially being used in our VSAT network using DVB RCS second generation, and using even DVB. They are using some of the coding and modulation techniques where you get advantage of EB by N naught by changing, we have discussed just now, by changing the from higher order of modulation, where higher spectrum efficiency, you come to the lower order modulation, or from lower order coding to higher order coding. If you go in both the cases, you have disadvantage in terms of bandwidth, but power wise you gain a very good power level, that is almost 10 to 15 dB of power advantage you get to maintain the same BER or symbol error rate using the same EB by N naught by changing the EB by N naught, same BER. So 10 to 15 dB is quite large number compared to the power control FMTR, either from the downlink or uplink power control. The other technique is data rate reduction, we just now discussed. There also you get quite a good amount of achievable gain, which is 3 to 9 dB of this order. But you know, it depends on the type of service or type of application you are using. For this type of service, suddenly you change the data rate for real-time operation, it may not be acceptable to the user. But it depends on the type of service or type of user. They may tolerate lower data rate, but try to maintain the availability as the same number. But again, as I said, that for file transfer or email type of non-real-time application, this could be used. It may take a little more time to transfer the volume of data, but you have the availability of the link. Site diversity, obviously you get a good amount. Our calculation shows that you get some amount, but by changing the distance much more, you get almost 10 to 30 dB. This committee claims. They have done some experimentation most probably, but you need 2 different stations, so your cost is increasing. Orbit diversity again is almost a simulation of theoretical idea, that is you have to use 2 satellites. Again, distance or different angles of that may give you a large amount of gain. Frequency diversity is also a terrible cost, because 2 separate frequency chains have to uplink and downlink has to be maintained at both the stations as well as at the satellite. Though you get a very large advantage, that is 30 dB. But the more as we see that commercially this coding and modulation is most popularly used, power control is also used, but people are not individually trying. They sometimes combine these techniques and get a higher advantage, which is called mixed FMT, combat large feed and combined FMT. So advanced communication technology satellite demonstrated combination of coding rate increase and data rate, which it was done in 1990s by US. It could show those days 10 dB gain. DVB RCS provides. DVB is digital video broadcasting, and RCS is return channel via satellite. So this is used by VSAT communication. What you see in bank ATMs they are using. This is a standard by European community. Provides such opportunity by combining coding rate increase and data rate reduction and uplink power control. There are many design issues, service requirement, performance criteria, and as we have listed earlier, monitor the link, BER, whether you decide whether open loop, closed loop, then estimate the next state, which needs a prediction algorithm, real-time prediction algorithm, and there are certain ITU standards on that. Control loop or change the link state using FMT, which needs a combination of which combination of FMT has to be used, what protocol to activate FMT, and the techniques, which is power control, signal processing, and diversity. So with all this, what we covered is effect of signal propagation through space earth medium, attenuation prediction, mitigation technique. So with this we close this propagation, signal propagation through medium and the effect and that mitigation for that. Thank you very much.